Hello, everybody. I'm just staring at a number that's going up at the moment as people join the webinar. So we'll give it a couple of minutes for people to get here. So in the meantime, if people would like something to do, feel free to say where you're joining from. That's always nice to see. So see people from around the world joining the chat. So Nick said, hey, and Naya. That's from California and New York, I think, these days. Czechia, excellent. Oh, yeah, that was Nick. Not provided. That's a new name. You got somebody from Ukraine. Welcome. El Salvador, New York, San Jose. There we go. Got some Europeans. This is a great advantage of doing these webinars on the web, is just the opportunity for people to join from around the world. So we're not limited by distance anymore, only by time zones and things. So we tend to run sessions at this time for people in the US. That kind of longitude, is that right? I think it's longitude. Hi, Aaron. So Samendra has asked if we're going to have more of these seminars. The answer is yes, definitely. I'm in discussions at the moment, planning out 2 new webinars that we're going to be producing next year. This webinar is, although it's called Advanced Querying Beyond the Basics, it should really be called Intermediate Querying. It's more advanced. And there's definitely a lot of tricks and tips here. But next year, we're going to produce, I think, a more advanced webinar still. So we've been getting some requests for sort of advanced aggregation pipelines and things like that. So we're going to do some webinars about that kind of thing. Hi, Southson from Cameroon. I apologize if I mispronounced your name there. We've got Yannick from Belgium. Fantastic. We'll just give it a few minutes. I got this number that's showing how many people have made it to the webinar, and usually it just starts to stabilize around now. And then, yeah, once that number stops going up, I will get started. Hi, Adnan. I get the impression in Pakistan it would be either very late at night or very early in the morning, right? And same with India, yeah. Hi, Manuel. So, number's still just kind of going up. It's slowing down, but the number's still going up. So we got Carson from Texas. I assume that's Austin, Texas. Right. So I guess we will get started. So hello, everybody. My name is Mark Smith. I'm going to be presenting this webinar to you today. I'm a senior developer advocate at MongoDB. I'm based in Edinburgh in Scotland. I didn't see anybody else say that they were from Scotland in the chat just then, but maybe we have somebody behind the scenes. We're very lucky that we have this dream team of Nick Raboy and Anaya Raisingani, who are going to be answering your questions during the webinar. And that is probably a good segue into describing how the webinar is going to be run. So the webinar will be recorded, and we will share the recording with you via email shortly after we finish. So I suspect by the end of the week. So you don't need to worry if you see a URL that you want to store, whatever, we'll provide that to you in the email along with the video. And yeah, if anything's going too fast, you can pause or slow down the recorded video. Obviously, you can't really, or maybe you can do that with the live video. I don't know. You will all be muted during the call because otherwise it would just be chaos. But we will be answering questions. So Nick and Anaya behind the scenes will be checking out the Q&A box. It's very important that if you have questions, you ask them in the Q&A box and not in the chat window. So they won't be monitoring the chat window. If you ask questions in the chat window, they won't see them and you won't get an answer to your question. So that's a little bit pointless. Yeah, I'll ask those in the Q&A window. Use the chat window for chatting to other attendees, maybe providing sort of impulsive feedback while the talk's going on. Sometimes I look over there and see a nice comment, and that's always nice. So finally, towards at the end of the webinar, there will be a short survey that will just pop up on your screen. Please take time to fill that in. It literally takes a minute, if that. And we really appreciate your feedback. It helps us improve the content of this webinar for next time. And it also helps us to work out what content we should be producing in future, where we should be spending our time. So without further ado, let's talk about what we're going to be covering in today's webinar. Here is today's agenda. First, we will recap some core knowledge about MongoDB just to make sure that everyone's on the right track. I'll recap some of the things that are important to understand as a sort of foundation for this webinar. You may well know quite a lot already in this section, but hopefully you'll pick up one or two things anyway. Next, we have what's really the core of this talk, where I'll spend most of the time talking about the aggregation framework in some depth. I'll introduce the aggregation framework, show you how it works, give you some tips for organizing your code, and I'll give you a tour of some of the more important components. After we've covered how to query your data effectively, I'll talk to you a bit about how to do it efficiently with a deep dive into some niche areas of indexing in MongoDB. And finally, I'll talk to you about how important data modeling is to your application and where to go to find out more information on that topic. So first, let's start out with a recap. Before Beyond the Basics, there was a talk that was once produced with the title Back to Basics, and it covered the fundamentals of MongoDB. We'll provide a link to that talk in the email that goes out at the end of the week. But what is more fundamental to a document database than a single document? This is literally my favorite document. I'm not kidding. It represents a 1-minute movie released in 1893. It describes this movie called Blacksmith Scene. This blacksmith is hammering on an anvil, takes a break for a beer, and then goes back to work. It's 1 minute long, and it's a TikTok video from 130 years ago, basically. So there's a couple of things that I'd like to highlight in this document. The first is that there's this field called _ID, which is the unique primary key for this document. Every document always has an ID, which uniquely identifies it within a collection. And it'll always have the name _ID, that primary key. And if you don't provide one, it'll be auto-generated for you. But if you have something that uniquely identifies a document that will never change, that has some kind of logical meaning, then you can supply your own value here if you want to, and it doesn't need to be one of these object ID types. Now, this document also contains several scalar values, and by scalar, I mean there's only one atomic value that can't really be broken up. So I guess you could break up a string into a series of characters, but that's not really the way we think of strings when we store them in a database. What's more interesting than these atomic values, these scalar values, if you're coming from a traditional table-based database, is that some of the values aren't scalar. So in this case, the cast and the director fields both contain arrays. Cast is an array with 2 values, and directors, although it contains 1 value, is still an array to indicate that more than one director can sometimes be found in this field, sometimes. So that's an important thing to note. I could have just stored a string in this field because it's only got 1 value instead of an array. And then in other documents that have more than 1 director, I could have stored an array with, say, 2 strings. But that's generally not a good idea. So it makes managing your data very difficult when you have documents with different value types stored in the same collection. So you can do it. MongoDB totally allows you to if you want to, but you should avoid it if you can. So an array is a sequence of items in order. The individual items in an array are looked up by their location in the array, 0 or 1, 2. But sometimes you want the individual items to each have a name. So here we've grouped together the data for that comes from IMDb. In this IMDb field, it's an object, or what we call in MongoDB a subdocument. So items in a subdocument have a name to look them up. So in this case, imdb.rating would be 6.2 and imdb.id would be 5. Subdocuments they're just a useful way of grouping related data together. Especially useful if you're going to store a subdocument inside an array, so you can have multiple records all stored together in a sequence. So after looking at that document, you may be under the impression that MongoDB stores JSON data, but that is not actually the case. Although you'll often see MongoDB described as a JSON database in lots of places, and up until recently it was still described that way on the MongoDB website itself. And it's a good way to initially think about MongoDB because it stores the same kind of structured data. It is JSON-like, so it's a helpful shortcut. But in fact, we store MongoDB in this format called BSON. Now, why is this important? It's important for a bunch of reasons. Mainly, BSON is just a better format for a database than JSON. It's more compact. JSON is just not a very efficient format, especially if you're storing lots of binary type data. It's also more traversable, so it doesn't require any text parsing to be done, which isn't very fast. BSON actually allows you to skip across the data until you get the value that you want, which is very important if you're quickly looking for something, if the computer's quickly looking for something in a BSON document. BSON also contains a bunch of extensions to JSON for accurately storing integral, floating point, and say financial data with this decimal 128, which you just can't do very well with JSON. You end up encoding them in strings. On top of that, it adds types for storing timestamps, which are very important to a database, and also efficient types for storing binary data and indexable GeoJSON types for storing location data, which can be very cool. So it's great that we have an efficient storage format, but that would be nothing unless you can find the data that you're looking for. MongoDB wouldn't be a general purpose database without its query engine. Now, you may have heard us refer to something called MQL in the past, which is short for MongoDB Query Language. And there are still some references, at least the last time I looked, to MQL in some of our blog posts and documentation. It's an ongoing task to kind of clean up that terminology. These days, we talk about the MongoDB Query API instead, because we've always had an API and not a language. So querying MongoDB is done through the various drivers that we support. And we attempt to make those drivers as native to the programming language being used as possible. MongoDB doesn't require coding queries as strings, like building up your query as a long string, that would just get sent to the database and passed into a data structure anyway that represents the query. Instead, MongoDB queries are built and sent to the database directly as a data structure. And they're sent to the server using the various API calls that are provided in the driver. If you're querying the database, you will probably use one of the three functions or methods that are on the screen at the moment: find one, find, and aggregate. These may be kind of spelt differently in your language. For example, find one is spelled find_1 in Python, because that's a natural way of naming a method or a function in Python, but they all work in similar ways. Find one takes a query and returns the first document in the database that matches the query that you've provided. Find is similar, but instead of returning just a single document, it returns you a cursor that conceptually contains all of the documents that match your query. And then aggregate is similar to find, but it takes a different and much more powerful data structure as a query. So it's just a different type of query that you provide. So first, let's look at the first two calls that I've listed here. So here is a query that looks up a document where the title matches blacksmith scene. And here on the right-hand side is the document that matches that query. It's that document that I showed you a few slides ago. So in this case, the query on the left is just a subset of the actual document that I'm looking for. It contains the title and the value that I'm looking for. But there are actually a bunch of operators that you can use to match partial strings or look for values that are higher and lower than your query values. And there's a bunch of binary operators that allow you to, for example, search for one thing or another. And I'm not going to cover query documents in too much details, so we won't cover that here. But notice on the right, there's a lot of information in this document. I can't fit it all on the screen. You'll have to trust me that it's all there. It's kind of underneath the slide. Let's say we didn't want all of those fields. We're only interested in one or two of them. In that situation, it would be pretty wasteful to send all of those extra bytes from the database to our client application. Something you can do with a find query is to add an optional second parameter. Again, it's slightly different between the different language drivers, how you provide some of these parameters, but mostly it looks a bit like this. So this second parameter that I've highlighted in green describes a projection. A projection either specifies fields to be included in the output, or it specifies the fields to be excluded from the output. In this case, because title, year, and plot all have values of 1, this is one of the first types. So I'm telling the query that I'm only interested in those fields and no others. So on the right, you can see that this document is a lot shorter than the one that was on my screen just before. It contains title, year, plot, and underscore ID. Underscore ID is special in that it's included by default. So even if I don't specify it as one of the things that I want included in this inclusion projection, it gets provided anyway. If you really don't want it, you can specify underscore ID as 0 in the projection and it'll be explicitly removed. So in most cases, it's more sensible to keep underscore ID around so that you can refer to the data that you're looking at in your application back to its exact location in the database. Moving up one level in complexity, here is a find query. So instead of find one, I'm now calling find, and this will do a query for every document where the year is 2010. Now this will return a cursor pointing to every movie in the collection that was released in 2010. But don't worry, because it doesn't load all of this stuff into memory in your application. It just sends an initial batch of documents to your application so that they're available for you to start looping through. And if you start to loop through them, when you get to the end of that first batch, behind the scenes, the driver will load more for you, and it will continue to do that until you run out of documents to loop through. So if you make a query for a huge number of large documents, you're not going to max out the memory on your application server. Although if you do try to take all those documents and put them in an array or something, then you are going to, that will happen. So notice that with both find one and find, if you provide no query document, oh, sorry, I say notice, but note that with both find one and find, if you provide no query document or you provide an empty query document, you get a cursor that points to every document in the collection, which can be useful if you want to do a batch operation on every document in a collection. Something else you can do with a cursor is to call count on it, which will tell you how many documents match the query instead of just actually providing the documents themselves. So in this case, our collection has 970 movies released in 2010. And again, you can provide a projection parameter, which reduces the amount of field data that you get back. So by specifying I want the title and I don't want the underscore ID, I'm just getting a cursor pointing to documents with a single field, this title field. And you can also sort your results. So again, this is a method on the cursor object that's returned. It's not loading all your documents into memory and sorting them in your application. It's doing it within the database. So it's just modifying the query so that in this case, the results will be sorted by IMDb rating with the highest rating first. That's what the -1 means here. It means that I want to sort it in descending order. If I wanted to sort it in ascending order, I would use a 1 as the value in the sort expression. So on the right-hand side, you can see that the highest rated movie of 2010 was Inception. which is not a surprise. It was an amazing movie, although I'm still not sure I fully understood it. What I'm more concerned with is that the second most popular title that year was Never Sleep Again, The Elm Street Legacy, which I suspect probably wasn't actually that good a movie. So there's something going on with the ratings here. So just to filter out a certain number of results, if I only want the first result, I can call limit on a cursor with the number of documents that I actually want. So if I'm looking for the top 10, or in this case, just the top 1, I can say that to MongoDB and it will optimize accordingly. It will only send that single document across the wire to my application rather than sending a batch of, say, 100 where I'm only going to be looking at the first one. And that is the end of the recap section. So hopefully you learned or refreshed your knowledge that MongoDB documents can have both array and object values. That's one of the things that makes MongoDB so powerful. You learned that it stores data in the efficient BSON format, which provides native types for numbers, dates, and binary blobs, among others. And you learned that you can do some interesting things with find, project, sort, and limit. And now let's advance our knowledge by diving into the aggregation framework. So the aggregation framework is another query endpoint in the MongoDB drivers, which is more powerful and also to some extent more complex than the find calls. The aggregation framework is actually one of my favorite pieces of MongoDB. So hopefully this section will get you as excited about them as I am. Now we've been looking at calls to find in the past section. This call on the left is the last call that I showed you. On the right is the equivalent call to aggregate, which is how you use the aggregation framework. So let me break it down. The first thing to notice is that the call to aggregate takes an array. It's a sequence of stages that will be conceptually applied in order to all of the documents in the movies collection. Now, in this case, the first stage is a match stage. I might call it $match or match. It's a little bit faster if I don't have to say dollar each time. Every one of the stages in an aggregation pipeline starts with $1 anyway, so it's a little bit of a redundant thing to read out while I'm doing a webinar. So the match stage, this match stage, filters out documents that don't match the query expression. So it allows through the documents that do match the query expression. The query expression document uses the same structure as find. So you can see this value that I'm passing to the $match in the $match field is just the same query as I've got on the left-hand side. So it's year and 2010. There are some slight exceptions. There are, I think, literally 2 things in the find query language that aren't supported in match for good reasons, but they're very niche. You're not likely to stumble across it. If you really want to know, go and read the documentation on this this stage. So instead of the match expression being one of 2 parameters to the find call, in this case, it's a stage in an aggregation pipeline. Now, once this stage has filtered just the documents matching 2010, the relevant documents are then passed to the next stage, which is the project stage. So notice that these match a similar pattern. The stage is an object with 1 field. In this case, in all of the cases, the name of the field is the name of the stage that you want to execute. So in this case, it's $project. It's the name of the stage I want to execute. And the value of that field is, in this case, an object containing all of the arguments to be passed to the $project stage. Some of the simpler stages that only require 1 value can just take an integer, for example. Now, this stage will remove all of the fields from the documents that aren't title or IMDb rating, and then those smaller documents will be passed to the $sort stage. Now, the $sort stage takes all the documents passed to it, sorts them, and then sticks them back in the pipeline where they're passed on to the next and final stage, which is the limit stage. It takes a number as an argument, as I mentioned could happen before, and it discards all of the documents after that number of documents have been emitted. And there you have it. That is the equivalent aggregation pipeline to the query on the left. And I realize it's a little bit more code, but the structure of these pipelines really makes sense to me. I find it such an intuitive way to write queries, especially once you've written a few and gotten used to it, especially the syntax that's required. So let me just explain more visually what's happening in this pipeline. So we start off with all of the documents in the movies collection. The match stage just passes through all of the documents that match the match expression. So in this case, all the movies from 2010. The project stage just filters out the fields that you don't want and passes those to the next stage, which sorts them. And then those sorted movies get passed one by one to the limit stage, which just rejects anything after the first document in this case. And that gives you the best movie of 2010. So just going over the definition of these stages for a moment with a couple of notes that I think are important. The match operator filters the documents to pass only the documents that match the specified condition to, or conditions to, the next pipeline stage. These are actually the first paragraphs from the documentation on the different stages, which I tend to find very useful in most cases. So it takes the same query syntax as find, as I mentioned, and you should generally place match stages as early in the pipeline as possible, because a match stage fundamentally is removing documents from later stages in the pipeline, which then makes those more efficient because they don't have to look at so many documents. The project stage passes along the documents with the requested fields to the next stage in the pipeline. And you can specify the fields as just existing fields with a 1 or a 0, or you can provide expressions that do calculations on data within each document. So you could add together two of the fields and store it in a third field. There's a bunch of stuff that you could do with projection to kind of create new values or just kind of restructure your document as you're passing it through the pipeline. So as I say, it restructures your documents. Do not attempt to optimize pipelines with this stage. So it would be very easy. If you're thinking about this very simplistically, you think that it's going to pass smaller documents through to the next stage, so then there's less data to deal with. That is not actually the way MongoDB deals with these aggregation pipelines. It's a useful way to think of them when you're writing them, but there's an optimizer behind the scenes that makes use of indexes and will sometimes even reorder stages if it's more optimal, and it won't affect the results. So there's a bunch of stuff going on under the hood. Don't try to reduce the amount of data within each document being passed through. If anything, you might confuse the optimizer and slow down your query. So usually a projection will be put at the end of your pipeline. You should put it as late as possible. Its real purpose is either reshaping a document for a later stage in the pipeline, or filtering out data so you're not sending so much data over the wire. That's the one optimization it will provide, is it reduces the amount of literal data being sent to your application across the network. Sort sorts all the input documents and returns them to the pipeline in sorted order. Again, you should place this late in your pipeline, partly because again, conceptually, if you haven't got an index to support it, it will take all your documents into memory, essentially do shuffling until it's ordered, and then it has to put them back in the pipeline again. So usually towards the end of a pipeline, you're working with fewer documents, and so it can make sort more efficient. We'll talk about sorting in indexes later on in this webinar. Finally, limit just limits the number of documents passed to the next stage in the pipeline. So why would you use an aggregation? I already mentioned that they're a little bit more verbose than find and the find and find one calls. But fundamentally, it comes down to numbers. So the find and find one calls, although very powerful in their own right, can only support 6 high-level operations. There's a match, project, skip, limit, sort, and count. And we've covered most of those in the recap. The aggregation framework, however, has 35 different stages. So there's a whole load of stuff you can do with it that you just can't do with calls to find and find one, including grouping and bucketing data, which again, we'll be covering shortly in this webinar. So I've highlighted in green some of the ones we've looked at. I've highlighted skip in here because it's conceptually very simple, but actually we didn't cover that. So let's talk about organizing your pipeline, because this is a bit dense. And even though I've structured it logically, it's still, there's a lot of stuff on the screen there, and it's not necessarily very self-descriptive. I have some recommendations for how to structure these queries in your code. And it basically comes down to this. So separate your stages out into separate variables. Give the variable as sensible a name as possible, not necessarily a short name, but a name that describes what the stage is doing. So here I've got a match year stage. I could have called that match year 2010, but I didn't for reasons that will become apparent in a few slides. I've got a sort rate by rating descending, limit one, project movie fields. They all kind of describe what they're doing. And then the way I can use these variables is to essentially recompose them into an array when I call aggregate. So here I've got my array or my list, and then I just provide them in order. And now it describes what it's doing, really. It says it's going to match on a year, it's going to project the movie fields that we want, it's going to sort by rating descending, etc. There is one limitation with this, which is that this is all very static at this point. Like I might want, if I'm building a website for all these movies, I might want a page for each year, like from 2000 to 2010. And so I'm not just going to always want to pass in the static value of 2010 each time. It's going to be a parameter that's extracted from the path to the page that I'm looking at. So in that case, we can create a dynamic stage by taking this stage here and converting it to a function. So now I've given it the same name. It's called match year, but now you can pass in a year as a parameter. And all it does is it constructs that stage with the dynamic data that I passed in as a parameter, and then it just returns it. And then when you use this within an aggregation pipeline, you simply call the function. And so that then inserts the stage with the value that you've passed in to the aggregation pipeline. So having covered how to organize your code a little bit, let's dive into another sort of a little bit deeper into the aggregation framework. Let's talk about analyzing groups of documents. So this is really the aggregation in aggregation pipeline. Instead of just filtering out a single document from a collection, I want to show you how to use the group stage to calculate values across multiple documents. But before we get to the group stage, I need to modify that match stage. So this is a new match stage to replace the last one, and it's now matching a year range. So I've added a few other things as well. So let's break it down. So first, because I want to add to match a range instead of a single value, I need to use the greater than or equal to and less than or equal to operators in my query. If you've written any kind of complex find query before or whatever, you've probably encountered these operators in one way or another. So I'm saying it's got to be greater than or equal to the minimum year that I'm passing into this function, less than or equal to the maximum year. That's relatively straightforward, but then there's some stuff beneath it that may not be immediately intuitive. So first, I'm also filtering out documents where the IMDb rating isn't a number. So we have some slightly dirty data in this collection. I think it was done on purpose. I think it's generally an exercise to show you how to use queries to clean up data. I could force non-numeric data to be numeric, but in this case, I'm assuming it's just dirty data, and I don't want those documents. So anytime the rating isn't a number, I'm just discarding it as kind of messy data. And then finally, I'm saying I just want movies, because there's the odd bit of like TV series data in the IMDb database that we're working with. And I'm saying I want documents where there's a minimum of 1,000 votes, because we're going to be looking at the IMDb ratings. And if you've just got one rating or two ratings, you can get wildly kind of outlier values. You know, if one person really loves a movie, but they're the only person that watched it, that's not really a highly rated movie. So I'm just kind of discarding those where not many people have watched the movie. There are some unknown movies that some people are very passionate about. So now I can insert this into the pipeline as before, and we can see that the most popular movie of the decade was The Dark Knight, which is another Nolan movie. And again, it's really good. I really enjoyed it. So let's get to the group stage. Now, this is the first paragraph from the documentation on this stage. It says it groups input documents by the specified _ID expression, and for each distinct grouping, outputs a document. The underscore ID field of each output document contains the unique group by value. Now, I don't know about you, but I don't find that as useful as some of the other descriptions that I've covered in this webinar. But don't worry about it too much, because I think it becomes obvious once you start to look at a specific example. So the main point to take away from here is that the group stage generates new documents using multiple documents as input for each output document. So let's start looking at an example. So I've defined this new group stage, and it groups by the year field. So you can see in this, the group stage takes a parameter, and in this case, it's I'm saying I want my ID to be generated from the year of the incoming documents. And what that means is it will produce one document for each unique value of year that it encounters. So as the documents get filed through this stage, it will pluck out the year and essentially produce a document for each unique value. So I've added it to my aggregation. So I'm just filtering down to a decade, 2000 to 2010, which is actually an 11-year group. It's not actually a decade, but let's not worry about that too much. And then I'm passing them through my group stage. And what we get is not super useful, but it is interesting. So what we have here, as I kind of described, we've got one document for every unique value of year. It's not super useful. The only thing we're really learning from this is, firstly, that the output is unsorted. So it doesn't automatically sort your documents as they go through. It's basically producing a document that for each unique value as soon as it encounters it. So one can assume from this that the first document that was passed through this stage was from 2003. And then the next year that it saw was 2000. And the year after that was 2006. You can add a sort stage afterwards if the order is important to you, or you can add it before if the order is important to you. And we'll cover that in a moment. So we do, apart from that, the only thing that we can see is that there was at least one movie produced in every year from 2000 to 2010, because otherwise there wouldn't be a document produced, because it would never have encountered that value. So here is where it starts to get interesting. Because each document is generated from all matching documents for that unique value, we can calculate values from all of the documents in each group. So here, excuse me, I'm calculating average rating from all of the ratings in that group. So in this case, $AVG is an accumulator operator. So if you're looking through the documentation for the other operations you can do, that's the magic incantation you want. They're called accumulator operators. Interestingly, to me, the average rating for each year is around 6.5 to 6.6, and it's relatively stable. It doesn't deviate that much. And I find that interesting because you would think that your average would be 5. So going from kind of 1 to 10, you'd expect your rating to be 5. So it's starting to look like people are more likely to rate a good movie than a bad movie, which is interesting. I find it interesting. So here I've inserted a stage before the grouping, which sorts by rating. So as I mentioned, the documents are passed in order to the grouping stage, which means that the first and last documents in each group can now be significant. Because we're sorting by rating, in the group, the first document that it looks at will be the highest rating, and the last document will be the lowest rating. And then we have accumulator operators for that, for plucking out the first document, for example. So because they're sorted by descending, I know I can take the first one in the group and know it's the highest rating. So here in the query, I'm generating a new field called highest rated title by just plucking out the title of the first document in this group. And then I'm taking the highest rated rating by plucking out the value of imdb.rating from the first document in the group. And that gives us the results on the right-hand side, which is that for 2000, the year 2000, the highest rated title was Gladiator, and the highest rating was 8.5, which is pretty high. And what we would get from this query is essentially the highest rated movie for each year from 2000 to 2010. Here are all the current accumulator operators available in MongoDB 6.0. We've covered average and first. You can count the number of values that you encounter in a group. You can push and generate a list from all the items in a group. That could be quite useful if you just wanted to group together all of the titles produced in a single year. You could use push for that and generate standard deviations and things like that. If none of these suit whatever operation you're trying to do, you can kind of brute force a result you can implement your own, essentially using the accumulator operator, and write your own JavaScript code, which will be applied to all of the documents in a group to be able to, calculate a value that you're looking for. But it's unusual. I don't recommend that you necessarily use that. So having kind of dived into a couple of queries, let's look at some tools for helping you build these pipelines. So I'm just going to do a quick demo here. So hopefully my screens are in the right order. Yes, looks like they are so far. So here, this is the Atlas Data Explorer. So if you're hosting on MongoDB Atlas and you've logged into your account, you've probably seen this interface. When you log into your cluster, you can kind of click through the databases on the left-hand side here and the collections on the left-hand side. And then, I've just cleared my aggregation pipeline. So that wasn't very sensible. But here's the document I was showing you before. Some people, I think, don't get past the Find tab, but there's a bunch of tabs here with useful features. You can create search indexes for building search engines on your data. You can generate indexes and things in this interface. We'll also give you some advice if you're modeling or querying your data badly. And if we can detect that. But there's this aggregation tab here. And this is essentially a developer environment for building pipelines. If you look down the page, we have all the stages in our query. So because I erased the pipeline, we don't have any stages, but don't worry, I'll recover from that in a moment. So first, on the right-hand side, we have a preview of all the documents that come out of each stage. So because we start off with all of the documents, it shows me a sample of some of the documents that are being passed in. And then I can select, say, a match stage down here. Match. And it'll fill it in with a helpful, well, in this case, less helpful template for what I could put in there. And I could put title, blacksmith scene. And as soon as I've got a valid query, it will start to show me samples on the right-hand side. Because there's only one document that matches this name, there's only one document in the sample. And then I could add another stage underneath. I can reorder stages. It's pretty powerful, but you noticed how easy it is to mess up by clicking on another tab and just kind of losing the pipeline that I was operating on. At least, yep, it didn't warn me. If you're going to use this in anger or you're going to use this significantly to build queries, build complex queries, I recommend not doing it in the Atlas Data Explorer. It's really only there for just sort of running ad hoc queries on your data and just kind of seeing what some sample results are. It's very useful, but it's got limits. But instead of using that, I recommend using this. This is MongoDB Compass. It's a free desktop tool that you can download for your favorite operating system. And it provides a very similar, as you can see, a very similar interface. So on the left, I've got my databases and my collections. And I can still look through my documents. That's the equivalent of Find tab we were just looking at. I can also evaluate my schema. I can do analysis on my queries, and pretty much most of the other stuff you can do in the Atlas Data Explorer. And here's the query that I was working with before. I'm going to try and make that one level bigger. There we go. So I have this is similar to the query we were looking at before. So the match stage here is the same one that we looked at before. So that's filtering down to a decade's worth of documents. And then I've got this bucket stage. Now the bucket stage is very much like group in that it generates new groups for different criteria. So before we were grouping on specific values of year. In this case, you could group, bucket allows you to group by a range of values. So I said I want to bucket by the rating, but my boundaries are from 0, which is the start. First boundary is at 2.5, second one's at 5, 7.5. So these are, I basically created 4 groups here, from 0 to 2.5, exclusive, from 2.5 to 5, exclusive, up to 10. And because it's exclusive, that's why I've added a 1 at the end here, like a 0.01 at the end, just to make sure that I can include any perfect movies that have a rating of 10. And then it gives me 4 documents that come out of the right-hand side. So I've got 14 documents that have a rating of 0 to 2.5. Oops. I've got 392 that have a rating of 2.5. I've got 4,000 documents from 5 to 7.5 rating, and then 7.5 and up, there's 1,000 documents. And again, this is kind of validating my theory that people prefer to rate movies that they like. They're not necessarily going to give it the top rating, but like a lot of people like to rate movies between 5 and 7.5. So even from a simple pipeline like this, we can learn quite a lot. And the reason I recommend using Compass to build these queries is because I can just save them into Compass. I can give them a name, and then I can load them again at any time I want to. I can also, this is true of Atlas Data Explorer as well. Once I finish my query, I can click on the Export Pipeline to Language button. It will give me the pipeline in JavaScript on the left, and then on the right-hand side, it gives me the same thing in Python or even Rust, which is one of my favorite programming languages. This doc expression allows you to create static types from dynamic data. It's really very cool. It's part of the MongoDB Rust driver. But yeah, and we can include the import statements and the driver syntax if we really want to, and you can see what that Rust code to run that query would look like. Once we've got that set up the way we want, I can hit the copy button, and then I can paste it into my favorite IDE, into my code. So it's a really good way to get started with queries, because you can really see what the results are while you're building your queries. If there's one stage in the middle that I think is maybe not quite right, or I want to see what the results would be without it, I can just temporarily disable this stage, and then we can see what's happening later on, which is that I broke the data being passed in. Oh, that's right, because now I've got these messy non-numeric ratings coming through. So I've broken the later stage of my query, but there are sense that sometimes makes sense. I can also in Compass explain my query, which will tell me how well it's using my indexes, and where the time is being spent when it's running the queries. And I can hit run to actually, instead of just looking at sample documents, I can hit run to see all of the results from running the query on all of my data, which is very useful. So imagine I just copied that query into JavaScript, but I like working in code. I'm not so happy. The problem with this is that it doesn't allow you to break up your queries in the way that I recommended, like creating variables and functions and decomposing your query so that it's easier to read and easier to maintain. So if you want to work that way, and especially if you already use VS Code, you need to know about the MongoDB extension for Visual Studio Code. So you can find it by opening up the extensions and searching for MongoDB. It's, I think, by far the most popular MongoDB extension. So there you go. And then hit install, and then it'll give you this extra icon on the left-hand side. You can use this to set up connections, to sort of pre-configured connections to different clusters that you have access to, maybe a development cluster, a staging cluster, hopefully not your production cluster. Shouldn't be making live changes to that, but it allows you to connect to them. It allows you to do some basic introspection, so I can see my collections. Once I start to click on the actual collection and look at the documents, they become a little bit unwieldy, but I can open them up and look at them. I don't think I can edit them and save them, but maybe that feature will be coming. I'm not going to try that in a live demo. But the real power of this is that it gives you these files called playgrounds that are JavaScript files that have the full power of JavaScript, and are already essentially connected to your cluster. So because I've told it to connect to my Beyond the Basics cluster that we were just looking at, I can use at the start to specify the database that I want to work on, and then I can build my functions. So these are, I'll make this a bit bigger again, maybe. There we go. So these are the same functions as I was describing before. So we've got match year range, we've got bucket by rating, and then my actual aggregation call. And then if I hit this play button up the right-hand side, I can just execute it, and there are my results that just come up in a new tab, which is very cool. And I'm going to show you a secret trick for using this as well. So one of the downsides to this is once I've deconstructed it, I can't take it back into Compass, right? Because I can't just copy and paste this code into Compass, because Compass only really understands JSON as input. But I am kind of compiling this to JSON here. And so when you press play, it doesn't print out the results of your last query. What it does is it prints out the results of your last expression. So if your last expression happens to be this array here without the call to aggregation, then if I hit play, it will give me just the query, but expanded. And when I'm going to copy that, and I'm going to go back to actually the Atlas Data Explorer. This works with Compass as well. And I'm going to, where am I? Aggregation. Create new from text. And then I can paste that in here. Confirm. And there's my query. So now it's passed it and broken it up into stages. So now I can go back to my GUI way of working. If there's one of these stages that I just want to tinker with and look at the results, I can do that here. So hopefully we have kind of solutions there for any way that you like to work. If you just like to work in the web browser, we have the Atlas Data Explorer. If you want something a little bit more persistent and powerful, we have Compass. And if you really like working with code, Visual Studio Code, definitely the way to go. That's generally where I spend most of my time when I'm building queries. So it's up to you. And that is the end of my demo of the various utilities for building aggregation pipelines. Let's carry on with the presentation. So I mentioned before that there are 35 aggregation stages, and that can seem a bit overwhelming. So I've tried to divide them into a taxonomy where I've grouped them by the way that they behave in a pipeline with documents passing through them. I happen to have the chat up on the screen, and Oluwafemi, hopefully I haven't got that too wrong, has asked, what about the shell? And they're absolutely right. With the MongoDB shell, Mongosh is really powerful. And while I've got it up on the screen, if you're using Compass, it actually includes the MongoDB shell down the bottom of the screen. So once I'm connected to my database, I can just click on that bar at the bottom and bring up the MongoDB shell and start typing commands that you'd run in the shell. So that's integrated with Compass. It's basically part of the demo. I apologize for missing that out before. So let's go back to the taxonomy. So, excuse me. Yes. So I've broken it down into these 7 different stages. There were 6, and then we added some more stages in MongoDB 6. So now there's a new kind of type of stage that I need to cover. So filtering stages, insertion stages, reshaping stages, joining, aggregation, sorting and limiting, and then redirection. So the first of these is filtering. We've already seen one of these filtering stages. There's a $match for filtering out documents that don't match an expression, or filtering just 2 documents that match an expression. The sample is very useful in that you can tell it, I want 1,000 random documents from a collection or from this pipeline, and it will just randomly select 1,000 documents and pass them through to the next stage. If you're working with a collection that's very big, and while you're building your queries, it's taking a long time to run them, then just stick a sample stage or even a limit stage at the beginning of your pipeline, and then they'll run much faster. You won't be looking at accurate results, but they'll run much faster. And then before you put that code into production, make sure that you take out the sample stage so that you're working with the whole collection from then on. But that's a handy tip for speeding up development. So yeah, we've got search as well that runs on search indexes. If you're running in MongoDB Atlas, we are in the process of launching a SQL stage that allows you to use SQL queries on your collections if you so wish. And those are your filtering stages. Then we have insertion. So these are documents and densify that allow you, they essentially insert new documents into your pipeline. Documents does it just for testing. So if you want to just pass some synthetic documents into a pipeline, you can do it in code. Densify is for data that comes in known intervals, like once a day. And if you're missing certain values, you can use Densify to produce, again, a fake document that matches a missing day and has a sensible value based on some calculation. We can reshape each document as it passes through the pipeline. So you've already seen project, which does simple reshaping by just removing fields from each document, but you can also use it to push values down into subdocuments or pull values up into the top level, calculate new values. So those reshape. You can also use add fields and set for doing many of the same things as with unset. Unset, set, and project are all essentially the same operation. And then we have some other values in there for just redacting values in your documents and things like that. Then we have joining. So many people aren't aware that you can join across collections or within a collection in MongoDB. It will find matching documents for each document that's passing through the pipeline, and then it will insert the values in an array into the document before it's passed on to the next stage. Super powerful. Then we have aggregation stages. So aggregation is really the act of grouping data together and making calculations. We've seen group and bucket. You get the idea. There's some other stages like that. Sorting and limiting aren't really the same, but they are relatively simple and they sort of belong together. So I've put those in a section together. Redirection is very important. So the merge and out stages will allow you to produce new collections or update existing collections from the results of running a query. So this is how you create materialized views in MongoDB to essentially optimize your application. If you're going to be calculating some values in documents and you're going to be reusing those much more, more than once, and they don't necessarily need to be absolutely up to date, then you can periodically produce, run an aggregation, save the results to a new collection, and then use that from then on. So you're not repeatedly conducting these maybe expensive operations on your data. And then finally, we have stats, which is not super important. It's just a way of exposing internal MongoDB data via the query language. It's sort of an ongoing program that we have. So, having covered the taxonomy at a high level, aggregation and sorting stages can use lots of memory. And if you find that your pipeline is running out of memory, there are a couple of things you can do. One is to make sure that any sorting that you're doing is supported by indexes. That reduces your memory a lot if that's the thing that's using the memory. And the other thing you can do is to provide this use disk parameter in your aggregation call. That will allow it to spool the data to disk while it's running the pipeline, and at the cost of it being a lot slower, will allow you to conduct these memory intensive queries if you need to. So I've already covered merge. This is a bit more detail in kind of how it works. In this case, with the query that I ran before, if I added this merge stage at the end, it would save those documents into a collection called recent movies. And it would update any existing documents with the same underscore ID by default. It must be the last stage in the pipeline. It doesn't make sense to have it earlier on in the pipeline. So, aggregation recap. That's really what we're going to cover in the aggregation section. An aggregation pipeline is a series of stages that are executed in order. There are 35 of them. It supports all of the stuff you can do with find and find one and more. And you should organize your stages into variables and functions to just make them more maintainable. Don't try to outthink the optimizer. There are some general rules as to where in a pipeline you should put different stages, but don't try to be clever by sort of projecting documents early on. So it's working with less data. If you want to become an expert in MongoDB aggregation pipelines, the aggregation framework, there is a free book that our colleague Paul Doan has written called Practical MongoDB Aggregations at this URL, practical-mongodb-aggregations.com. I learn something new every time I go to that book. It's been written or edited and reviewed by a bunch of my colleagues who are much smarter than I am. So definitely check that out. So I'm assuming you already know that you should index fields in your collections to support your queries. So I would like to talk about some slightly non-trivial topics very quickly, because even though this is a slightly longer than usual webinar, I'm actually running behind time. So let's start with compound indexes. Compound indexes are indexes specified on more than one field. So here I'm running a match on year, rating, type, and votes, and I can create an index that is maybe sensible for that, to filter down those values to year, type, and votes. I don't need to match on all of the fields, but it's the ones that are most selective, so the ones that are most likely to reduce faster, so that then if there's a later manual stage of like scanning through the documents, it's not working with so much data. The ordering of those fields matters. So year, type, and votes will support queries on year, year and type, and year, type, and votes, but it won't support any that skip any values. So type and votes, or year and votes, you have to start at the beginning, and then you can move, you can use any of the following, like directly following fields, and it will support those queries. Sorting can also be done with indexes. I've made a couple of references to this already. If you have an index that supports your fields and in the correct order, then it can use the index to sort your data rather than pulling everything into memory and sorting it in memory. So this can really be a huge efficiency improvement in your application. You can sort on any prefix of the index or any complete inverse of the prefix. And what I mean by that is, again, it's year, year and type, or year, type, and votes all in ascending order, or it will support them all in descending order, in the exact inverse, but it won't support a mix of the two. So it won't support year and type in descending order with votes in ascending order, or anything else like that. So it's just worth knowing how, when you're generating these indexes, the order can be very important when you're sorting. It's possible to index fields which contain arrays. So this is something that's more or less unique to MongoDB. So in this case, MongoDB will create a value in the index for every item in the array, or in the arrays that you're indexing. And we call these indexes multi-key indexes. So in this case, I've created an index for cast, which I've got one document here with two values. And now when you search for either of these authors, the index can be used. Or I can search for an exact match of the array. If you do that, it doesn't manage to just pull out a value from the index, because the index is kind of flat. What it will do is it will find the first item of the array. That's what it'll look up the first item that you've provided in the index, and then any matching documents, it will then do an array scan to check that all the other values match. So it's not quite parsing in the array that you're searching for and plucking out a single document. It's a little bit more intensive than that. So be aware that if you apply these indexes to a large collection of documents where the arrays are very large, then your index is going to be huge. And it's very, very important for your indexes to fit in memory. They're an optimization, so you want them in memory so that you can work with them in a sort of random fashion. If they go onto disk, then you're going to be paging data in and out of disk, and that's really going to affect the performance of your application. On the topic of memory usage, let's talk about wildcard indexes. They were added in MongoDB 4.2. Sometimes you have documents or sub-documents where you don't know exactly what fields are going to be present. So a metadata field is quite a good example. Maybe it's just something that's pulled in from another data source, but you'd like to be able to efficiently look up documents using any of these keys. So here I've got this user metadata, and there's lists, which is an array, or sorry, likes, which is an array, dislikes, which is a single string, or age, which is a number, or even there's just a string for the whole metadata thing. It's a string instead of a subdocument. Now I can create this index using this command at the top right. So the magic incantation here is the $*** that says basically user metadata is going to be a wildcard index, which means I'm going to recursively index anything that appears in or beneath the user metadata field. It should be immediately obvious that these can get enormous very quickly because it's a recursive thing. So you're essentially taking the whole subdocument and indexing every single item in there. So these are for very specific cases where you really don't know what's going to go in there. Don't use them to replace a sensible indexing strategy. They get very big very quickly. They're there for very niche use cases. Don't get overexcited by them. So that's a quick run through of some of the things I think are important about indexing. Be aware of compound index field order, and also how that's going to affect your sorting, because you can invert your sort order from what the index supplies, but you can't mix and match different orderings. And be very careful about index size. That's like rule number 2 of MongoDB. Rule 1 of MongoDB is data that is accessed together should be stored together. So it's about modeling your data in documents. And then the second rule is probably make sure your indexes fit memory. And finally, for that reason, use wildcard indexes very carefully. Now, I really wanted to cover data modeling in this course, but as you can see, we're already like 5 minutes past the hour. So I've been talking for an hour now. So I want to point you at a couple of important resources for data modeling. So the first is, if you come from a relational background and you haven't done a lot of data modeling with MongoDB, there are some they're not even tips and tricks. There is just a whole philosophy around how you model data in MongoDB. And it's something that you build a little bit with time, but also you can get really up to speed very quickly by reading this blog post on MongoDB patterns. So if you did want to take a screenshot to read something immediately, like I would be doing that now. This is a series of, I think, 11 modeling patterns that just kind of warn you about things or show you general patterns for sort of data access and data storage that will be optimal for MongoDB, rather than splitting your data up across multiple collections. Once you got bored of this, once you've learned all you can learn from these blog posts, do Google for MongoDB anti-patterns. There's a series of sort of related anti-patterns that are just things to watch out for in your own in your own data modeling. Make sure you're avoiding those anti-patterns. So data modeling is very important for storing and retrieving data efficiently. There are apparently 12, I think there are 11 official patterns now, because we used to have a pattern called the bucket pattern, and now you should just use time series collections. If you're storing time series data, check out time series collections. And some examples are extended references that essentially allow you to avoid joining. I'm sorry you have to go Oluwafemi, but don't forget you'll get the recording up to the end later on in the week. And then we've got document versioning that enables migration over time. So I've mentioned the Building with Patterns series of blog posts and Paul Doan's practical MongoDB aggregations book. There are lots of other resources, and I'd like to highlight 2 of them. I'm probably going to be done with this section in another kind of 3 or 4 minutes. First is MongoDB University. You can find it at university.mongodb.com. 2 specific courses I recommend you look at are M121, which is the MongoDB aggregation framework, which will really make you an expert with that whole thing, and M201, MongoDB performance, which will help you understand indexing and modeling in more detail. Then there's community.mongodb.com, which is where the people who develop MongoDB hang out with the people who develop with MongoDB. So it's where our users hang out with our developers. It's a very cool place. It's not just for asking questions. So it is a place to go if you have questions, but it's also a place to just tell us what you're up to. It's really exciting to see things people have built with MongoDB. We get very hyped up about that. And you know, if you're interested, we'd maybe like to, once we learn about it, we'd like to promote that on our streaming channels and things like that. That may be a thing. And finally, in terms of next steps, like if you really want to put some of this information into practice and really become an expert, go build something. That's what you should always do when you're learning new things. Go and use this knowledge to build an app or optimize an existing app. I'm excited to see what you build. So that's basically the end of the content for this talk. Thank you very much for being here. There will be a short Q&A session, but I think Ashwini is probably just going to bring up a poll now. So if we could just, if everybody could answer the questionnaire, we would really appreciate that. So you can see it's not very long. I think there's only 5 items in it. Six items. And while that's up, I will look at the Q&A panel and see if I can answer some of these questions that come up. Does actual data get fetched and processed after each stage? If yes, is there any limitation on the data that can be passed from stage X to stage Y? The answer to that is no. So although conceptually you want to think about it as all the data being passed like physically through each of these stages, what's really happening is it's converting it to index lookups and kind of transformations. It's sort of as a big, I would call it a mess, but it's really an optimal kind of execution pipeline. So no, there's no specific limit on the data that can be passed from X to Y. It's all streaming. There is, as I say, there are certain operations that really do require your data to come into memory. So if you're doing a big sort on data that it doesn't have a supporting index, then potentially it's going to have to pull all the documents at that stage into memory before passing it on to the later the rest of the execution of the pipeline. So that is something to think about, but there's not a hard limit, as it were. It's just based on the limitations, the memory limits on your machine and the configuration of your MongoDB server. Martin has asked, is there a big difference between find and aggregate in performance? And the answer is no. So in fact, because the find optimizer is, because it can't do so much, it's actually like, and it's a bit older, it's highly optimized. And for certain types of queries, it could be ever so slightly faster. You know, we've found some sort of niche places where we can provide real sort of extra optimization. The aggregation framework is clever enough that if it recognizes something that could just be run as a find sort limit operation, whatever, it will literally convert it into the equivalent find call and use that optimizer on it. So, I mean, I suppose there'll be a couple of milliseconds as it does the transformation, but it's all just done under the hood for you. Manuel has asked, are aggregation functions pipelines executed automatically when the collection changes, or can you set them up so they do? The answer is yes and no. I mean, maybe no and yes would be a better way of putting it. So no, aggregation functions are executed when you execute them. So they're only done on demand if your application is demanding them. They're not driven by the database. However, MongoDB supports change streams that allow you to listen to a collection for changes. And so you could monitor a collection and in your application automatically drive an update, a new aggregation when the data changes, or much easier is to use, if you're hosted on Atlas, is to use Atlas App Services and create a trigger, which just allows you to have a JavaScript function that's executed whenever your data changes, and then you can create your materialized view if necessary from that trigger. So yeah, you can do other stuff in Atlas triggers too, like you can make HTTP requests. So if you wanted to combine with the data that's just changed with an API call to another service, like you can do all that stuff in there. It's super powerful. Is create index the newer version of ensure index, or are they the same? I have to admit, I don't know, is the answer to that. It's been a while since I wrote this talk. It's possible ensure create index will fail if there's already an index, whereas ensure index won't. But I honestly don't know. I'm sorry. If anybody, if Nick or I want to chip in there, like I feel like that's a stupid hole in my knowledge, so I should have been able to answer that question. Olufemi has asked, which is better in my experience, single compound indexes or multiple indexes? It depends on your use case. So multiple indexes they'll be bigger, but they'll also support reversing the order of the sort or something like that. If you're sorting on name and age, or age and name in different orders. Whereas, yeah, compound indexes, as you've seen, like if you're always going to be sorting or querying with a certain prefix, like a certain order of the indexes, the way that your fields, the way that you're looking them up, then a compound index is going to be faster, as well as because it's just a single index lookup rather than I think I answered that question. And then finally, Can has asked if you want to compare a tuple in MongoDB, what should you do? Get document that's AB in 1, 2, 3, 4. I'm sorry, I don't quite understand the question. I apologize for that. If you would like an answer, like, feel free to drop into community.mongodb.com, tag me, and either myself or somebody, we can have a conversation and hopefully answer that question. Brad has asked whether aggregation pipelines execute server-side, and we're all talking about server memory. And I apologize if I didn't make that clear during the talk. That's absolutely correct. Yes, your query is executed on the server. The client actually, the client is reasonably complex in that it's managing a pool of threads and trying to optimize the transfer of data, but it doesn't do any querying on the server side. The querying is, the client side, but the query is always executed on the server side. Emily has asked if there's any data dictionary views in MongoDB, as in Oracle, so that I can review all of the collections, files, and data types from one query. Not that I know of. But you could write relatively simple code, I think, to loop through the different collections and gather the data that you're looking for. Nick may be typing an answer. I'll read it out if something comes. No, the data is changing as to how this is going to be answered. So I think I will leave it there. If I didn't satisfactorily answer your questions, please feel free to drop a question into community.mongodb.com. My name is Mark Smith. Feel free to tag me. And thank you very much for being here. I really look forward to finding out what you're all building and what you've built with the stuff that you learned in this webinar. Thanks very much.